All right, this is a promise signing sheet. Yeah. So. So on Monday, so no, I'll just put it like this in class and then. And on Tuesday, on Wednesday, John Nichols, and he's going to come and talk about neutron, positive neutron. So Monday, I'm going to do like machine learning, artificial intelligence stuff. So the Wednesday lecture won't be about that, but then Friday we'll have a quiz thing. It's like a thing about machine learning, like data, like automated data collection, and then machine learning from that set, and then they go through a whole routine on Google Colabs. We use that. Anyway, so it'll be kind of interesting, I think, but probably not that challenging, but it's something we can see how to do that. Anyway, so Ben's here.
Hey guys, what's up?
So
Sorry I'm late.
that's all right. No, you're on time. Anyway, so I got the papers like here, like this paper, that one's there, and the supplementals like next to it.
Yeah.
Then there's this one supplemental, that one. You can make them bigger.
Okay. I have a little presentation that
Okay.
I gave.
All right, that's
for
great.
lunchtime.
That's pretty good.
Maybe I'll start with that and then we
Yeah.
can go to the paper.
All right, yeah, so the stuff's there anyway. If you want.
The EPS presentation.
Oh, yeah, that's great. That's perfect for this. The table is pretty short. It is. I don't know why they make this so short.
I can put it up there.
Yeah, if you want, you can unplug that, unplug the projector. Does that have an HMDI? Anyway, you can put it here if you want to do that. So Ben's you've been here like a year, right? Or, all right, I was trying to figure it out, but
Time is flying.
yeah. So he's done a lot of stuff, like in the short lifespan he's had. But
I'm not that old. I'm not that old.
he was gonna talk about what's the other thing was like the nanocomposites, and then it's like stuff with Schweitzer, the prism theory, and all this stuff.
I could do that, but
Yeah, no, I mean anyway, we didn't do that one, but
Okay.
basically that's a pretty good paper too. Actually, I used that for homework in here
did you? Okay.
like last year or the year before or something. So anyway, he's done quite a few things for someone that's like pretty young. Anyway, I thought this was a pretty good thing. I like this project he did. And it was like copied afterwards by like.
Yeah, I'll tell that story.
It's interesting to hear the story about that. So I'm gonna go this over here.
When does class go till 10, 11?
10 to 11:05.
Okay.
But let's see. Here, project. What is it? No, wait, this thing isn't. Oh, you did do it. Okay, so it should be projecting. Let's see, this thing's, the camera's on, right? They do that. Right?
Are you on Zoom also?
Yeah, I'm on Zoom too. Oh, yeah, that's gonna be a problem.
Yeah, we can just do the paper. It's fine.
Well, so I think they can see in a little window on it. I'm just
My
recording it.
computer's not HDMI, it's not going into HDMI mode. So
Oh, so it's not.
Yeah.
All right,
I can wing it. So
all right,
let's go back to this.
that's pretty weird. Do you want to try it one more time, or you just want to go with that? I mean, wait, let's undo this first, right? You did that routine, though, right? Yeah. Yeah. Don't you have just an HMDI plug on this? No, it's not. All right. Dongled up. All right.
Because this should already start recognizing it.
Maybe that line's dead.
Up here, hold up.
Oh, okay. That would explain why it's so short. All right, that works. Okay, sorry. All right.
Classic.
Yeah, so he was in, I should say, like, he did his PhD at UMass, him and minors, like a rheology guy. Then like took kind of had Koga, who's like the nail composites person. And then had to British Columbia. They did like bio stuff, I think, in Canada.
Yeah, so hey everyone, if you haven't met me, I'm Ben. Yeah,
You went to school in Case for undergrad.
yeah. So I did my undergrad at Case in polymer science engineering. Now I'm a chemical engineering professor here. Started about a year ago, so just getting started. But yeah, my background's in polymer science, polymer processing, and I did a lot of X-ray scattering also, which I guess you guys have been learning about in class, right? So I actually got involved in X-ray scattering when I was a grad student. And then what I'm going to talk about today is my work. I went and did a postdoc at the National Lab at Brookhaven, which has a synchrotron facility. So this is basically a giant X-ray generating source where we can do a lot of these really interesting experiments and look at polymer dynamics and polymer carbon. What have you guys been learning about so far? I guess what are the last few lectures been on? Dynamic light scattering. Okay, yeah. So this what I'm going to talk about today is dynamic X-ray scattering experiment, and the physics are essentially the exact same, except instead of using a laser light, which has wavelengths of a couple hundred nanometers, something like that, right? We're using X-ray radiation on the electromagnetic spectrum, and those wavelengths are much shorter, about 0.1 nanometers, something like that, right? So we're orders of magnitude higher energy, lower wavelength. That allows us to look at a different regime of dynamics and structure, right? This is kind of a little presentation I gave, I guess, at a AICHE meeting a while ago. Oh, it was the virtual one. That one sucked. But yeah, so this is summarizing some of that work that I did. So I'll just give a little overview of what the project was, what we were interested in, and then we'll actually look at the paper that we published and talk a little bit about that, how we put these experiments together into a full study, all right? So our research group at the time, again, I was a postdoc at Brookhaven National Lab as well as Stony Brook University, and our group was really interested in correlating and coupling behavior from the nanoscale all the way up to the macro scale in polymeric materials, right? So polymers are really interesting because they're made out of these macromolecules that have sizes of about 10, 20, 100 nanometers, something like that, right? But when we use them, we're playing around with things on the macro scale, right? Things that are millimeters or even meters big, right? So we want to understand structure, properties, and dynamics at that small level so that we can correlate it and build it up to having something that has good mechanical properties at the bulk level that we live at. Again, we were really interested in these particle polymer composites. So what happens when you take a polymer material and put in little nanoparticles, inorganic materials, right? How is that going to affect the properties and behavior of our materials? So the key thing in our group that we were interested in was advanced manufacturing and processing of these materials in out of equilibrium environments. So I start with my polymer matrix and I have my polymers and I put those things together. Maybe I push them through an extruder, or maybe I mix them in a batch mixer. Maybe I'm 3D printing them, doing something like that, right? That's a dynamic process. Things are moving around and changing really fast at certain timescales. How do I understand that so that I can take my bulk materials and get a final part or composite of these two things, right? Okay, so again, we were at the X-ray beamline at Brookhaven National Lab, and our technique that we were using to understand this behavior is a technique called X-ray photon correlation spectroscopy, or XPCS. This is basically what I'm going to be talking about today. So XPCS, again, is very similar to dynamic light scattering. So as I'm talking about this, I want you to think about what you guys learned with DLS and how it may be similar or different from this technique, okay? So essentially the way this experiment works is we start with our material system. We've got some matrix material, and then we've got our little nanoparticles or our probes floating around in that material. They are moving around with some thermal diffusion, or they may be moving around due to some processing or something, right? So this is a dynamic system. Got my polymer and my particles, and they're all floating around at some time scale and on some nano length scale, right? So what we do is we take that material in the bulk state, we stick it right in front of the beam line. We shoot this X-ray, so it's coming out of this big ring, and then we focus it and we shoot it right at our material. Key thing here is that this is a coherent X-ray beam, all right? So all of those wavelengths are all timed up very nicely in this form. It hits our material, and then the interaction of that X-ray with these little objects in our polymer is going to scatter that light, right? So just like light scattering, you look and see how those X-rays interact with your material. They're going to bend off in some other direction, right? And when that happens, we have this detector at the other end, a 2D aerial detector that's going to collect those photons that have been scattered, all right? And I hope you can see it from this picture, but that comes out and looks kind of like this. It's a fuzzy little speckle pattern, and we literally call that a speckle pattern, right? So our area detector is just collecting those photons that got blasted out of our sample after transmitting through, all right? Now, the speckle pattern is maybe doesn't look that interesting. I don't know. Some people think it looks kind of pretty, but it's actually very useful, important information. What it's doing is it's essentially encoding the local environment or kind of position of these particles at that one instant in time, right? We've got light coming through, blasting off, getting collected on the speckle pattern. That speckle pattern shows what the arrangement of those particles was at that time. And if you see in the schematic here, we've got a bunch of these speckle patterns all backed up next to each other. So what we do is we just turn on the detector and we basically film a movie, a high frame rate collection of these speckle patterns in time, where each one is encoding and showing basically where these particles are in time, all right? So it's a way to kind of literally make a mini movie of the movement of all those little particles at that nanoscale. Now, again, a movie makes sense. We can see it. It's in real space. We can see things moving around. But as we know in scattering, this information is in reciprocal space, right? Q, inverse nanometers, something like that. So just by looking at those speckle patterns, we can't actually really tell what's going on in our real space that we exist in, all right? So we use a data kind of processing technique or protocol to get out the information in this real space regime. And the way we do that is we take these speckle patterns, we look at how the intensity varies as a function of time, and we get these kind of crazy plots here. But what we can do is we can integrate across that, and basically we look at the time or temporal variation in the intensity at some scattering vector Q on our detector, right? That's the length scale we're looking at. And then from that, we can calculate or generate what's called an autocorrelation function, which is going to correlate those intensity variations in time. And what that comes out to is it looks like an exponential decay like this. We're at short time scales, so frames that are all right next to themselves. If things aren't changing very much, they're going to be highly correlated, right? So that means our function is going to have a big value. So up here, it means that from frame to frame, things haven't changed that much. And if I think about that on the nanoscale, that means that those things aren't really moving, right? But as I go longer and longer in time, because things are moving around, those frames start to look a lot more different. And that function starts to decorrelate or decay over time. Where at long time, my image from the beginning and my image at the end don't look like at all. They're completely different, which means that my arrangement has fully reorganized itself at that nanoscale, right? So from this function, we can actually fit it and calculate what the relaxation time is of that process, right? So when you do that and you measure the relaxation time, you're basically looking at the diffusion or diffusive behavior of that particle on the nanoscale, right? So this experiment, do all this work, and essentially all you get out is this time scale that tells you how fast that particle is diffusing in the nanometer length scale. So that's why I basically say we're measuring particle diffusion in that complex fluid, just like we are in dynamic light scattering. But here we're looking at things on the order of, 1 to maybe 100 nanometers, something like that, right? Cool. Makes sense. Took me over a year to figure out this technique, right? When I started my postdoc, they're like, go do XPCS. And I was like, I know those 4 letters, but that's about it, right? It took a long time for me to kind of grasp this concept of how we do these experiments, what we're actually looking at, and what the data looks like, all right? So here's an example of what some of that data might actually look like. These are autocorrelation functions that you can generate. This is from a really nice paper, Lyndon Archer's group at Cornell, and they were looking at the diffusion of these nanoparticles in polyethylene glycol. In PMMA, sorry. So they were looking at the diffusion in a glassy polymer, and they could modify the surface of those particles to change their diffusion. But essentially what they saw is a collection of these correlation functions, whereas you change the molecular weight, the time scale or the diffusion behavior of those particles is going to change in that matrix. That makes sense, right? We make our polymer more entangled, thicker network, those particles are going to move around a lot differently, right? But this is a quantitative technique or a way to actually calculate that. These things are, like a couple nanometers. You can't see that. You can't do microscopy. You have to go in and use X-rays to figure that out, right? So the important thing about this technique, again, is the X-ray part, right? We're looking on that scattering detector, and depending on the angle that those photons are scattering at, that's the length scale we're looking at, that Q space, right? So what we typically do with this data is we collect all of these at a bunch of different Qs on our detector, and then we plot the relaxation time as a function of Q, all right? And if we see this kind of scaling behavior down here at the bottom for this 2 kilodalton post-polymer sample, we get a power law exponent of -2. So the relaxation time scales with Q to the -2. And that is indicative of Stokes-Einstein diffusion, just thermal diffusion of a particle in a liquid material, right? Now, what we've found is, what these guys found, and what I'll talk about as well, you can get a different type of scaling where now the relaxation time scales to the power of 1 with the Q. And that is a ballistic or linear type of behavior, right? I've got a certain amount of time and it moves a certain distance. That's a velocity. That's not a diffusion. Diffusion is meters squared per second. Velocity is meters per second, right? So in these type of systems, when you change the molecular weight, the fundamental physics of how these particles are moving around changes completely. We go away from this diffusion-dominated regime to this kind of collective or ballistic type of regime. And this has been a huge discussion in the field right now about what this actually means, right? So I don't have all the answers of why that happens, but the data shows it. So it's really quite interesting, right? So I'll give a quick rundown of what we did in this study. This has a lot of the figures in the paper, and then we can look at the paper itself. And then I'll talk some funny stories about the paper. So this was a cool project because we were actually being funded by Henkel Corporation. So I don't know if Henkel makes a bunch of super glues, adhesives, curable resins, that kind of stuff, big German company, right? And they were interested at utilizing this technique and these facilities to help better understand the processing of their actual industrial materials, all right? So again, they're interested in curing processes. How do you take something from a epoxy, little syringe, squirt it out, you want to stick 2 things together, right? That glue has to cure and harden. How long does that take? What's the processing conditions you need to solidify that? We were going to use this XPCS technique as a way to measure that curing reaction in real time, right? So that's literally the sample. Like this was just epoxy off the shelf that they had and were using actually on the factory floor. They designed it through just formulation science, mixing things together. They had no idea how it worked or what worked in it, right? So we were trying to go back and do some fundamental science to understand this material. But basically, this is an industrial adhesive. And one thing that's important about it is it's got a high volume fraction of these aluminum trihydrate filler particles. And those are in there to modify the viscosity. and also play with the thermal stability. So they're an actual functional component of the material. But in this case, they're going to be our dynamic probes, right? We're going to be watching how those fillers move around in the matrix as it's curing, right? That's a really important part. Yeah, so we literally just threw that thing into a temperature cell and we ran it through a pre-cure step and then ramped it through this thermal cure where you heat it up really rapidly and then hold it at 120 degrees for 30 minutes. And that's what it says on the bottle. That's how long it takes to cure, right? So we wanted to validate and see, could XPCS also give us information about that curing process at the nanoscale rather than at the macro scale, which is the typical type of experiments we would do, right? Okay, so bear with me. The really interesting part about this research is this kind of out of equilibrium nature. And what that means is that the dynamics and the structure of our material is changing on the timescale of our experiment. So we can't just do one of these XPCS experiments and get the relaxation time. The relaxation time is changing as we're taking data, all right? So the way that we actually observe that is on these two-dimensional plots here, which are called two-time correlation functions. So instead of doing a correlation function from just that first frame in the figure across all the other frames, we do correlations at every frame in between. So we create basically a 2D matrix where we're just comparing all the data that we have across all times, all right? Again, that took me a really long time to get my mind across as well, but it makes sense in this 2D picture. Essentially, what I want you to look at is this diagonal here. If we go along that diagonal, that's the average aging time of our experiment, where we start our experiment here and we end it down at the end. So if I track along that, that's basically the progression of that curing process. If everything on both sides of that diagonal is symmetrical, that means our timescales are not changing in our experiment. It's at equilibrium condition, all right? So in the pre-cure state, we were really happy to see that things are moving around. They're not changing on the timescale of our experiment. There's one relaxation time that defines this material system, right? And we calculate that by doing the autocorrelation function. Anyone have any idea what's going to happen if we have an out of equilibrium system? What do you think this figure is going to look like? Close. There will be some disymmetry in it. You will still have the same behavior on each side of the diagonal, but what you'll see is that it now bifurcates out and it changes as you go along that diagonal, right? So basically the scale bar, the color here is the amount of correlation that we have. So in these systems, our system is decorrelating very quickly. It's changing from red to gray very quickly. But as you see, as we go out in time, that correlation starts to hold out for much longer time periods. So it stays correlated until longer times. Yeah.
Just because the axes are very different, do you know like how long that first one would correlate? But that one goes out, 16 seconds.
So that's a great point. So these experiments are really tough because we're making our own movie, right? When you take a film, what do? You leave your camera on for a certain amount of time, right? But you also play with the exposure time. So we can calculate how long, or we can tune how long we want that axis to be by playing around with the exposure time and the number of frames. And we kind of have to know a little bit going into our experiment how long we expect that to do. Because you're right, if I just took a video in this little chunk right here, it would change, right? And we actually did that. We didn't see any change. Like, oh, cool, nothing's happening. And we're like, let's go a little longer, right? And once we expand out that time domain, then we start to see the relevant physics and the relevant relaxation times. So yeah, these experiments are very difficult because you have to play around and, fiddle with the acquisition parameters so that you can get these figures to show up over a relevant time domain. And it all depends on your material, right? Who knows if you have something that's relaxing fast or slow. These ones are really tough to capture because they're changing so drastically, right? This is relaxing very fast. And that's basically the curing process there. What we saw was that the relaxation time slowed down a lot, orders of magnitude. So we had to be really careful about our design of experiment, how we were able to capture that time scale. Yeah. Possibly. So if it reconverges, what does that say about the dynamics? Start to speed up again, right? If you have very narrow, thin lines, that means it decorrelates really quickly. And if you have big, kind of chunky, dark domains, that means it decorrelates really slowly, right? So that's the relaxation time we're looking at. So not in this experiment, but some other interesting experiments people are doing is they're looking at cyclic loading of rubbers or nanocomposites. Basically, they're pulling, de-pulling, and you can watch those type of behaviors where things speed up and slow down depending on the strain or how much you yield those materials. So those come out, I have some data on my computer. They basically look like checkerboard patterns because you get these regions where they're correlated and decorrelated at certain frequencies that you're yielding that material. So yeah, those are really weird. I'll tell some stories about data analysis in a second, but there's a reason I'm not showing those right now. So, right. So these pictures are cool. We can throw them in our paper, whatever, but they don't tell us anything about the actual physics and the timescales, right? So how do I get that relaxation time out from this figure? So what we do schematically is I basically track along that average aging time, and I make a little slice or a cut. And I say, what is that decorrelation going to look like right along this line here? Essentially saying, if I started my XPCS experiment at aging time 1, aging time 2, let me look at the correlation from that point in time, right? So we're doing these slices along that. And then those slices come out into these nice exponential decays, these now one-time correlation functions that is describing the dynamic process and dynamic behavior, right? So we like to call this quasi-equilibrium dynamics. It's not necessarily at equilibrium, but we do the integration in the assumption that things are not changing at that one time that we're looking at from the process, okay? So that was really cool because the colors show, this is exactly what we were seeing on the plot, right? As we increase time, that characteristic relaxation time that this dynamic process is decaying at increases. So basically the particles are moving slower and slower and slower as we go through that curing process, right? So funny story, I'm colorblind. And these originally in Python, when we're doing this analysis, it's not a colorblind friendly format. And my postdoc advisor was sending me all these figures and we were trading stuff together. And he's like, what do you see happening? Like, nothing, dude. They're all the same. Because what are you talking about? You don't see the red and the orange one? I was like, what the hell are you talking about? And so we had to find, there's one line in Python you have to put at the top that changes it to like colorblind friendly mode. And then once we did that, I was like, okay, now I can write the paper. But before I had no idea what he was talking about because everything looked the exact same to me. Anyways, so yeah, these should look good now. So that is a way for us to analyze this process. We used a little bit different form. So we modeled this correlation function off of a stretched exponential that's defined by some parameters that have to do with our experimental setup. But the key thing here is really this gamma. That's the relaxation rate or the rate that that function decays at. It's the inverse of the relaxation time. The only reason we did that is because it's easier to write it on one line rather than have a division sign. The other key component in there is this gamma value. Gamma is a stretching or compression exponent. So simple exponentials always decay down at a certain rate, but sometimes there's other dynamic timescales that define that process. So you may have to stretch or compress the exponential, and we can do that by that power factor right there, right? And we found that that mattered, right? These are not simple exponential decay functions. They're actually kind of more rich in their physics, so we had to apply that function. But the thing we found, again, we plotted that relaxation rate versus Q. I'm talking, this is the important thing, that tells us what type of dynamics we're looking at. All linear functions. We didn't see any diffusive behavior in these systems. All of it was ballistic correlated motion. And the cool thing here is that we can now basically get from the slope of this, our like quote unquote diffusion constant for that system. Again, it's not a diffusion constant because it's not diffusive dynamics. It's some velocity VP, which we just call the like particle velocity or something like that, right? But what you can see is that at 85 degrees in that pre-cure state, we've got a certain slope here. At 111, it increases, right? So if my slope is increasing, what's happening to my dynamics? It's getting faster. It's getting faster when I'm heating it up. I thought it was curing. What's going on here? So that's actually the part before you get to the curing reaction. So we're heating it up. The curing reaction hasn't initiated yet. This is just like thermally induced behavior, right? You heat up something, it moves around faster. So we actually saw an increase in the dynamics before we hit that critical curing temperature. And then once we hit 120, where the reaction starts actually curing, the dynamics dropped a lot down to the slow behavior. So there should be a plot kind of describing that whole story. Yeah, right here. So in blue, that's the temperature. During the temperature ramp, we saw an increase in the velocity, an increase in the dynamics. So things are moving around. We're heating that system up. And then literally as soon as we hit 120, that thing drops like crazy over almost 2 orders of magnitude in the dynamics. All right. So the cross-linking reaction can be tracked in situ at the nanoscale using that process right there. And we proposed that this was more powerful. This was a powerful technique because one way we would do this is by like mechanical testing, right? Maybe rheology or DMA or something like that. But once something cures, it's really hard and stiff, right? It's hard to tell how much stiffer and harder it actually gets once it gets into that regime where it's kind of locked up as a solid. Here, we're probing at the nanoscale, right? Much finer, smaller detailed behavior. And what we could see is that that curing reaction progressed much deeper, thousands of seconds into that process, whereas in rheology, we would have just seen it plateau and just hold out, right? So there's still something going on at that nanoscale about the cross-linking and the curing reaction that we can actually measure with this technique. And then that was kind of our hypothesis in the beginning. I should have shown that first, sorry. But our hypothesis was, again, in the pre-cure state, these guys would be moving around real fast. You'd have high mobility, low cross-linking. And then once that epoxy cured to form a nice adhesive, those things get stuck in the matrix and they don't move around a lot, right? Yeah, so that was really exciting. We like this because it's a commercial material, right? We just took this off the shelf, we threw it into the beamline, and we got nice quantitative data. And you could use that information going forward if you want to process it differently, try different cure reactions, different cure chemistries, whatever. And let's try and pull up the paper now because we also correlated it to some other techniques, and that was a nice crossover as well. Any questions? I ripped through that real quickly. Last time I gave that talk was 4 years ago, so I'm really happy I remembered it all. No, because I don't think we could track it that fast. You need a couple temperatures along the way, though.
Yeah, we had temperature.
Yes. Yeah, we could have. Yeah. Yeah, we didn't do that, but I think we had to. We probably have to. No. Yeah, I think you'd have to play with the heating. We would try to do a rapid heating rate.
Yeah,
so.
but it's just the. Oh yeah, well, it doesn't equilibrate.
Yeah, it's not equilibrating. Yeah, so those are some of the figures we put in, showing that kind of drop in the dynamics from the one-time correlation functions as we started going through that ramp. So things speed up. And then once you hit the cure state, they cure out. That same plot there. Yeah, okay. So this is another one. We looked at this reaction under DSC, differential scanning calorimetry. This is another way to track these kind of reactions because they give off heat as they go through that reaction state. So we put our thing through the exact same heating protocol in DSC, and we saw that the heat flow followed that increase and then that decay as well after we hit the curing process. So the thermal properties of this heating reaction seem to correlate very nicely with the nanoscale physical dynamics of this reaction as well. And then the blue one is just showing, we did a scan right after it's cured, the whole thing has been kind of eaten up. And those are just the natural heat flow changes in the material. Yeah, so some fun stories about this. These experiments are pretty quick. Again, we're looking at behavior over a couple thousand seconds, but you got to remember we're taking thousands of frames at frame rates of, 10 to the 2 to 10 to the 3 hertz or something like that. Literally, each one of these experiments is about a terabyte of data. And we were doing like 2 or 3 days worth of these experiments. So at the end of the day, you get, I can't even physically show you, it made my brain hurt, but the amount of data in these experiments is absolutely insane. So I collected all this data in probably 2 or 3 days. Took me 6 months to analyze it and write the paper because it's that data rich and intensive. But that's why it's really fun. You don't have to do a lot of work, and then you get a ton of cool information. Just sitting through it is ridiculous. So this one was funny because this paper, I actually didn't do these experiments. They did them right before I joined, but they had that challenge. No one wanted to analyze it. There's so much data that the grad students were like, oh my God, I can't do this. So they're like, all right, get the postdoc, cheap work. So I showed up, typing it up. And I think I wrote this paper in like 1 or 2 months, something like that. We just got it out the door because we've been sitting on this data for years and never got to it. So yeah. Yeah.
How much of
A lot. So in light scattering, you're shooting a laser at your sample, right? That's got some energy to it. X-rays are orders of magnitude higher energy. One thing we face a lot, especially in polymers and soft materials, is beam damage. So you're shooting this X-ray, really bright, a lot of photons. You can literally like fry through material and degrade it in real time. So most of the thing that we do in these experiments is we test basically the dosage of photons that we're giving to the sample. Because sometimes we'll do an experiment and we'll just fry it out, and the dynamics we see won't be representative of our material. It'll just be if some lost it out. I don't even know it. I don't know what happens, but you can like artificially cure things. You can destroy polymer chains. You can do all these things. So what we do in these experiments is we start at a high dose, and we see kind of this artificial decay in our dynamics because we're burning our material. And then we start lowering the dose down progressively until we see a point where now our dynamics are independent of the amount of photons or the dose that we're giving our sample. So we have to go through this whole cycle of testing those dose independent dynamics so that we know what we're getting. You may ask, why don't you just blast it with full power? Oh, well, if you blast it at full power, you can see a lot, right? You got a lot of photons coming through, your signal's really good, right? So as I decrease my dose, my signal starts looking worse and worse, and it's harder to pick out those structural features because I just don't have enough intensity, right? So that's the trade-off. We want to find the highest dose where we get good scattering signal, but also independent dynamics of burning that thing. So we'll probably spend an entire day doing that, playing around with exposure times. We can attenuate the beam, so the beam just comes through on its own, right? But we put these silicon wafers in to break down and block some of those photons. So we'll try these series where we'll put in different silicon wafers and see. That's how we attenuate the beam. So a funny story with that, as Greg asked me to start getting ready to tell you guys about this, I was rereading these papers, and I got an email from a PhD student at Columbia who was like, hey, I just did some XPCS experiments. I read your paper. We had some questions because we think we're getting beam damage. Can you tell us what protocols you use in this experiment to avoid the beam damage? Because we didn't list it explicitly because we had a lot of conditions. You're kidding me. I've done this in like 4 or 5 years. So I went back, I dug up our old spreadsheet where we did all those calculations, and I had all that information. I was like, you are very lucky today, my friend, because yeah, I have it all here. Should have reviewed that shit. But anyways, yeah, so it's a lot of work, but it's super important, right? And I don't know if people at the beamline are skipping that step now and just going and doing their experiments and saying, oh, look at all this cool stuff, right? No, you have to do a lot of pre-input ahead of time to figure out what's going on and save it. Don't throw out. I know it's terabytes of data, but try and save it. Google can hold on to it or whatever. So Any other questions? I'll tell some other funny stories about this last minute. So, yeah, so we published this in 2020, right at the beginning of the pandemic, actually. I'm glad we got that out. But in that meantime, again, some other groups were doing very similar stuff to what we were doing. And also we're sitting on their data. So this paper came out in 2021, so shortly after that. This was a really nice paper, again, utilizing the same resources at the beamline I was working at. So Lutz and Andre are the two beamline scientists. Hilmar Korner is actually a research scientist, or he's a project leader or something at AFRL up in Dayton. So he works at the Air Force Research Lab. And they're really interested in epoxy resins because all those carbon fiber composites are made out of epoxy, right? And they go through so much trouble trying to figure out how to get those things to cure into really strong composite materials for Air Force, airplane wings, all that kind of stuff, right? So they were interested in using this technique to see if they could also understand the nanoscale curing of epoxies, just like we had done. But they made a much smarter system. They went and said, hey, let's make a model material that we can actually get some better physics out of, right? Ours was just an off-the-shelf epoxy from Henkel. They were the ones who were funding the project. This was in that kind of step back based off of what we did to do a little bit more fundamental research. And what they did was they took a very common epoxy resin. This is an EPON something. They basically use this for all their composite research. So they know everything about the rheology, the thermal behavior, but they don't know about the nanoscale properties, right? So again, they've got bulk rheology, DSC, and now they're trying to throw in this XPCS experiment to correlate all this data that they've collected for these bulk macroscopic properties and how that informs the nanoscale properties. So what they did was really smart was they took silica nanoparticles with a diameter of about 15 nanometers in the system. I forgot to mention the fillers in our material were about micron size. So orders of magnitude larger than those nanofillers. This is really nice because now we're on that length scale where the XPCS is actually picking up interesting Q dependence, right? A Q space and real space is like 1 to 100 nanometers, something like that. So you're really now actually probing that individual silica particle moving around in the matrix, whereas we were kind of looking at these huge fillers just floating around. And that's probably why we saw those collective dynamics. We weren't at the length scale where diffusion is important. And the other thing that they did here was they only added in 1 volume% of these fillers. Very small amount, right? So if you imagine and looking at the nanoscale, I've got basically a silica particle kind of isolated on its own. That should be a nice environment for diffusive dynamics. Our material was big ass particles and a lot of them. So they were kind of banging into each other and the dynamic environment just completely different. So exact same experiment, different materials, hopefully different physics. I haven't looked at this in a while, but yeah, they did pretty similar analysis, blah, blah, blah. Oh, so this is what's interesting. So now they're plotting that relaxation rate as a function of cure time. Each one of these columns here is basically one of those slices that I showed in my plot there. So if you were to zoom in, that one column would be one correlation function where they could fit that relaxation rate. So they're seeing, again, as they cure this sample, that relaxation time is increasing and the thing is actually curing. But what they did is if you go in and look at the Q dependence in this regime down here, you get this type of behavior. Now they're plotting it against Q squared. So if I see a linear dependence between the relaxation rate and Q squared, that's diffusive dynamics, right? Now, if you look at the Q dependence out here, it's no longer at that same scaling behavior. It actually goes to Q to the 1. So they were able to identify that transition from from diffusive dynamics to ballistic dynamics as a function of the curing, which is cool, right? Start out, you've got just Stokes-Einstein diffusion, a molecular liquid, and then you cure it into this polymer melt, everything gets trapped, and now the dynamics, the fundamental physics of that relaxation process changes, and they could track it really nicely, whereas we were not able to see that transition. So that was really kind of a cool thing about this study. And as I said, terabytes worth of data. You can make as many plots as you want. I God, so
Well, they also got the complex viscosity. I'm using to know if
they did, so I guess I skipped over that.
So
Yeah, so they used basically Stokes-Einstein theorem says that the diffusion of that particle is going to be related to its size and the viscosity of the medium around it. So they use the diffusion constant to back calculate out what the viscosity would be at that point. So they could actually now not only just track the dynamics, but they could track the viscosity growth in their material, basically using what we call a microrheology approach.
they matched it up with both rheology, right?
They did, yes. Yeah,
Yeah, so it's interesting.
yeah. So they were able to calculate that nanoscale velocity, and then they did so this is the viscosity from XPCS, but they have some rheology.
They just skip through it.
Was it this one?
No, it's not.
Was this one?
Yeah, so.
Oh, yeah.
So it's down to. I think on the surface.
Yeah, so they're looking at the same physical property, the
If you color
viscosity.
you won't be able to see this.
Yeah.
It's just like nothing.
So then that's really powerful because you're taking a bulk measurement at something at macro scale that we can see, and you're correlating it down to some physics at the nanoscale. Huge range of length scales where that behavior is correlated and related to
But
it.
also you have this big bulky viscometer, right? And then you have this, just the beam going through.
That's-
the same number.
That's
right?
true. The rheometer costs probably $20,000 and the X-ray beamline costs $500 million, something like that.
It's a little bit more.
Okay. I don't know. My PI was really funny. He's like, we're doing these experiments. So the other thing is, when you do these experiments, you have to apply for beam time. This is a government facility run by the DOE. So you submit a proposal. You say, I want to do these experiments. It gets reviewed. They say, hey, cool, we got a good idea. Come on in. They'll give you 48, 72-hour time slots where you need to come in and do everything at once. And that, once you walk in the door, the clock starts. So if you want to maximize your time, you have to work 24 hours for like 2 or 3 straight days. I probably shaved several years off my life working there from pulling consecutive all-nighters, doing these experiments, because if you sleep, you don't collect data. So, and
The rankings of the journals, so it starts out with their paper.
Oh, yeah.
So that's a good journal. That's better than macromolecule. Then they came out with a kind of a better.
This
kind
one?
of a better paper, right? But it's later, it's copied your work, but it's in a lower, kind of macro is a little bit lower journal. And then the third group comes out and puts it in Nature, which is the top journal.
so
It's really weird how that worked out, and how they got away with that.
So the other thing is there's only a few facilities around the world where you can do these experiments. There's 2 or 3 here in the US. There's one in Japan. There's one in Germany. So there's a very small community of people doing these experiments. My guess is they're all talking to each other and keeping an eye. Like when we go to meetings and there's the XPCS talks, there's like 2 or 3 of them. You can see automatically what everyone's doing, right?
Plus Koga, one of the guys.
I don't think he knows these guys.
Okay, all right, but it's like a Japanese connection.
It might
a
be.
little bit.
Yeah, but they were very smart. They said Koga et al. Performed XPCS. Yeah, so this was the third paper that came out that basically redid. It was submitted a little earlier than the Air Force guys, but it was basically the exact same experiment. And they said, you always have to put this in a paper to convince the reviewers that you're doing something new. So they said, yeah, Koga et al. Performed XPCS experiments on epoxy resins, and they showed it as a powerful tool for observing the dynamics from liquid to solid states. They observed the evolution. However, owing to the fact that the densely dispersed fillers, they only had ballistic motion. They couldn't see the full curing process, and they didn't discuss any change in the movements. So they basically said we were lazy and just tried something off the shelf, right? So they come through and now propose almost the exact same system, this EPON with a crosslinker, little silica particles. I honestly have no idea.
I mean,
They got submitted like 1 month apart, so they must have been doing.
Nature, like. All right.
Okay, this is Nature
Science.
Science Reports, so this
Okay.
is like a
Alright.
little shell version. But one thing that these guys did that was a little different, which I won't get into now because I don't fully understand it and it's kind of complicated. They looked.
Copy exactly the equations you had. but
Oh, yeah.
They're just reproduced,
So what they were also looking at was dynamic heterogeneities. So I think you mentioned earlier what happens when it comes back in. And sometimes when you make these correlation functions, you'll look and see that it's kind of jaggedy, which means locally what you're looking at is kind of very rapid changes in the dynamics from fast to slow, fast to slow, fast to slow. Some people would say that that's noise, but in fact, those are actual real physical processes that are occurring. And essentially the way I think about it is this thing is curing so quickly, it's changing from a liquid to a solid. You can develop these kind of stress concentrations internally where things get really quickly trapped and then maybe off somewhere else, something rearranges and then it's able to move really quickly and fill in that space. So these dynamic heterogeneities are kind of thought of as like long-range avalanches of kind of weird movement internally in the system. And those come out into these weird undulation patterns. If you want to analyze that, you have to calculate another correlation function on top of that, which is this chi value, which is the dynamic heterogeneity property or something. And yeah, I don't know how to do that analysis, but that's kind of the step that they took, was they noticed that they got these weird heterogeneities forming and could quantify that as well. So oh, yeah. So that's why these are important, right? If you're trying to cure a part uniformly, get really nice macroscopic behavior, probably don't want to, right? You would want that curing process to occur, everything to settle in real nicely on its own, right? But depending on the material properties, the chemistry you're using, these might show up. And I don't know any other way other than scattering to investigate and identify it. So I think what the finding is from here is that they were only seeing it at long times, right? So it was kind of this late stage heterogeneity that was appearing. So either you cut it off before those things start showing up, or you change your chemistry, run the experiment again, see how you can mitigate it, right? So that's kind of the power of this technique. But yeah, Greg, I think that's why this was enough different from the Air Force paper. The Air Force guys really went all in on the rheology, the GC. These guys spent a little bit more time working on the data analysis with the actual SPCS experiments that they had. But you said, it's funny, they use the exact same equations, they do the exact same experiments. That's something that we as scientists who use this facility have to justify to the government, right? They spent all this money, they invested to build this thing, and everyone's going to go do the exact same thing. Well, what's new, right? You write this proposal and you're like, we're going to do what these guys did. And that's kind of the whole point of the facility, right? We want to make this capability so we can investigate new materials. We don't necessarily have to change the experiment like every time, right? That's not novel. What's novel is looking at new physics, new materials that we could never look at before. That's how you kind of pitch it for them. Because again, if I said like, oh, we're going to do the exact same thing that these people did a month ago, that's not new. You really need to say what you're going to find is going to be new. What materials you're going to look at new. If the experiment is the same overall. Yeah.
What are some of the applications of figuring out the dynamics of the
Yeah, so one would be trying to chart that curing process. So again, like I said, with rheology, it's kind of hard to see those late stage evolutions because the thing just solidifies and you can't really see anything further. But if you're interested in kind of longer time behavior, setting behavior, other thermal cycling, that kind of stuff, then this technique is able to access those behaviors. The other thing I'll say about dynamic testing is you're defined by your geometry, right? You either need to put it in a rheometer or you need to put it in a DMA. This technique allows you to do, we called it in operando measurements. As long as you can get that X-ray beam in, then you can do experiments on any type of processing that you want. You could do it with an extruder. So my other project, if I can pull it up really quickly, was actually applying this to 3D printing. Yeah, so when I showed up, they're like, hey, just analyze this data quickly on this model system. But the real reason we were doing this was to try and investigate the 3D printing of these materials. So here we actually built a 3D printer that we could stick onto the beamline. And then we went through and we were extruding these filaments out and then looking at the curing process in real time using that XPCS. And the reason that's important is because in 3D printing, The speed that you print at is important, the pressure is important, the deposition time. You cannot replicate those in a rheometer, right? So if we want to see processing dependent behavior, we can do this in operando in real time. And the idea here is, if you have a 3D printer that you're printing in your garage or in your lab, bring it to the beamline, do it just like you would there, and then get this real quantitative data and information on that. And the real cool finding from this technique, which we found was, real quick, blah, 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 blah. Yeah, so we tracked the dynamics under UV. So we were UV curing it. So we would deposit the filament, hit it with UV, initiate that curing reaction. Initially, you can see a really fast decrease in the dynamics, and it's a function of the UV intensity that we use, right? So if we cure it lightly, they'll slow down slower. If we cure it really fast and hard, they drop really quickly. But we kept that measurement on. Oh, she left. But we kept that measurement on for several hundred seconds after we printed the filament, and we saw that the dynamics continued to evolve and still decay. When you're trying to 3D print something, you're trying to go as fast as you can, one layer, another layer, another layer, another layer, right? But from our experiments, we found that the structure and the dynamics are still evolving hundreds of seconds after you printed that layer. So it's by no means, you can't just print it and move on. It's still alive, it's still changing. And that's going to be a big consideration when you want to come and put another layer on top. You're going to disrupt that structure, and it's going to evolve in some new pathway as well, right? So I think these experiments were interesting because we were able to define that time scale. So if you want to wait 100, I think it was 10 minutes in between filaments is when we started to see it equilibrate. So technically you'd have to wait 10 minutes in between printing one layer to get a real true equilibrium part, which no one is going to do that, right?
So if you want them to stick together, you don't have a little bit of plane.
So that was the second project we did. Yeah. So then we investigated how do you time up that print time with having enough mobility at the top so that layers will fuse together. And we started doing some experiments on those multi-layer ones. And again, the 3D printer was there. All you got to do is move it in front of the beam. And hopefully we're then can investigate interlayer diffusion and trying to improve parts like that. So. Cool.
Does that, let me just show the last of the ones I put up. Does that, they did a reflectivity, does that mean?
Yes, that one I had not seen before.
That's actually one of the better of the papers. Could have been in Nature probably.
I know it was in soft matter.
Yeah,
Yeah. So I'm not as good at reflectivity, but you can either do transmission experiments where you shoot straight through a bulk material and kind of probe that scattering volume from one end to the other. You can also do experiments where you're reflecting off of a surface, and there you're actually probing just different layers of that different geometry, and you can achieve different setups as well, right? What if I'm talking about a casting or a coating process where I want to make a nice thin film? Looking at a bulk chunk is not going to be that useful. Here, you can actually lay that out, get like a film epoxy coating, and then use reflection X-rays to look at the dynamics as well. So this is still kind of a new, when did this come out?
This year, I think it's.
Yeah, so there's a group in Germany who's been coming to the beamline at Brookhaven, who've been really pioneering this, call it GI XPCS, so grazing incidence XPCS. And again, class is over, so I guess I don't have to talk about it. But yeah, it's like way crazier with just the interference patterns that you get, the way you analyze the data, much more kind of juvenile experiment compared to those stuff.
Thank you. You guys have questions, whatever. So, yeah, if you have something to stick in with you, just the guy.
Not yet. I mean, beam time's hard to come by right now, so.
They had 2 or 3 days to collect all that data.
Oh, yeah, so that story was, yeah, I was, so we would just pull like all-nighters. You'd sleep for like 2-3 hours, come back.
Anything in retrospect that you wish you would have did differently within those days?
Slept more, yeah. It's tough at the end of the time where you're like, we got to finish these, and then if you don't finish, then you have to wait another like 4 or 5 months until you get another chance. So the preparation is a lot, making sure everything's all ready to roll, getting it done, and then you can sleep for like a week afterwards. So cool, that was fun.
The reason I was curious about like continuous operation, like curing.
Yeah.
Is I worked in a like polymer CPVC extrusion plant.
Yeah.
And there would be like unknown quality issues during the extrusion
Okay.
process. And I don't know if it's related to this, but it's sort of